Good evening, everybody, and thank you for joining us this evening for our presentation on hydrogen. I'm Rick Stuckey. I'm a member of SOIL, Save Our Annoy Land, which is part of the coalition to stop CO2 pipelines. And you might not think that hydrogen and CO2 have a whole lot in common, but it turns out that most of the projects involving hydrogen hubs that the government is working on will require a carbon dioxide pipeline to remove their waste products. So I'm going to go in a little bit now to why there is this great deal of interest from the government and industry on creating hydrogen hubs. One of them is the Midwest Hydrogen Hub, which is was just received a grant of $1 billion approximately for various different projects in and around the Midwest. One of those is going to be in Whiting, other one's in Indiana, other one is up in Illinois, close to one of the nuclear power stations, so they can use the nuclear power. And there are several other ones that are in the pipeline. The amount of information about these projects is rather slim at the moment. We'll get into some of them maybe a little bit later on. So I want to go into what's behind all this interest amongst the industry and government on hydrogen pipelines. I'm going to share my screen. Okay, so why all this interest in hydrogen? Well, first of all, it's the most abundant element in the universe. It's the simplest and most abundant one. Just one proton and, well, usually two of them together and a couple of electrons. The reason for the fascination is that it is extremely high in energy per kilogram and extremely high in terms of, well, it gets the most energy per liter. But a liter of hydrogen, as you'll see, doesn't go very far. I'm going to take this diagram on the right-hand side and blow it up a little bit next so you can see it in more detail. Oh, there we go. The axes are changed a little bit by name, but the same ideas. One is the power by kilograms in the bottom axis, the x-axis, and the y-axis is power by liter. And you can see here in the middle are the things we are used to seeing as our power sources: diesel, gasoline, kerosene, and not far away, propane, butane, and so on, ethanol. They have a moderately high energy per kilogram and a moderately high energy per liter, and they're very convenient in the sense that they're liquid and you at room temperature, and you can pump them into your cars and so on and get a lot of energy out very quickly and very easily. Over here on the right-hand side, you can see hydrogen, and as a gas at the bottom there, it has a very, very low energy per liter. You know, a liter of hydrogen at atmospheric pressure is, you know, not much in it. If you pump it up to 700 bar, about 10,000 pounds per square inch, you get a lot more of it. And if you can cool it down to a very, very low temperature, about minus 260 degrees Celsius, you get liquid hydrogen, which is even more dense in terms of power per liter. And if you were going to try and build a space rocket, for example, and you were very concerned about how much energy you could get per kilogram, because that's what has to be lifted off the launch pad, you would, clearly your first choice would be liquid hydrogen, especially since you're only going to do it once or twice a year, and you could create all the infrastructure you need to do that in one place in Cape Canaveral, and it'll be your preferred choice. If, on the other hand, you were Elon Musk and you intended to run these space rockets off from several different locations and multiple times a week in some cases, you'd want to have a more convenient fuel, and he chose to go to methanol, which is still fairly dense, but not as hard to handle. Moving on from there, you see natural gas. Natural gas, again, just like hydrogen at the atmospheric pressure, has very little energy per liter, but you can pump it up to says 250 bar, 250 atmospheres, and get quite a lot more energy per liter. And you can cool it down again to a very low temperature. And liquid natural gas, you're in pretty good shape. You're almost approaching the energy per liter you would get from diesel and gasoline. Just by the way, look up at the top left side, you see anthracite there. That's basically coal, and you can see that it has one of the highest energies per liter. It's very, very dense and has a great deal of energy in it. And down in the bottom left-hand side, you see the battery storage techniques. Lithium batteries, very low energy per kilogram, very low energy per liter. Zinc air, a little bit better in terms of energy per liter, but still very low on the energy per kilogram, which is why making your electric car go a long distance is a serious challenge. Anyhow, you can see here why hydrogen has a lot of attraction there. The other thing, of course, this chart doesn't show is the pollution that comes out of these products. And for over here, it's roughly proportional or inversely proportional to the amount of energy that's in there. Moving on from there, let's talk about how we get hydrogen. There are several different processes. If you look at the bottom part, the gray square here, you'll see virtually, this is 95% or more of the hydrogen being produced today comes from one of these two sources in the bottom. Coal, when combined appropriately with water and a lot of energy, can give you what we call black hydrogen. And it's black because it creates a large amount of pollution, carbon dioxide particularly, but also other pollutants. And those are usually emitted to the atmosphere, which is bad. Moving up a little bit, you can take what is probably the most common approach, which is to take methane, natural gas, lots more water, and lots of energy, go through a similar chemical reaction, and produce slightly better hydrogen. It's brown in the sense that it is not as bad as the black stuff, but it still, in the production, creates a large amount of carbon dioxide, which is emitted to the atmosphere. So those account for a vast amount of hydrogen in production throughout the world, but there are other alternatives. You can, for example, take the brown hydrogen process, go through the same chemical reaction with the same amount of methane, hydrogen, water, and energy, and clip onto the back of the process a carbon capture operation. So here we're getting to the carbon dioxide pipelines. A carbon capture process which is not trivial. It's quite complicated in the sense that you've got other pollutants coming out of natural gas, sulfur oxides, and so on, that need to be separated, and the product has to be dried, and that's what goes on in the carbon capture process. Then you pump it into a carbon dioxide pipeline, take it 100 miles away or more, and dump it underground, just like you would do from the ethanol plants. So it's theoretically cleaner, and even more energy is required for that carbon capture process than was required when you were just doing the regular brown methane, brown hydrogen rather. And in many ways, you'd be better off just, if you're going to burn the hydrogen, burning methanol, burning methane rather, and not even going through this whole process. But there are processes which need hydrogen and not methane wouldn't do. The other alternative, major one, is what we call green hydrogen, which is to take water and electricity and split them into hydrogen and oxygen by just passing electricity through the water, and you produce therefore a product with no carbon in it at all, clean green hydrogen and clean oxygen, which you can emit to the atmosphere perfectly satisfactorily. But there are problems with that. Those are looking at the two processes that are primarily being considered. As you can see, they could only cover 5% or so of all hydrogen production. There are actually many more ways of doing it. You see the brown and black at the top. The gray is just the steam methane process with no capture. Blue is where we say we're adding carbon capture onto that one. Turquoise is a different kind of a process which still takes methane and CCS in and doesn't produce it produces carbon at the end rather than carbon dioxide, and carbon is much easier to handle, but it's expensive and difficult. Pink hydrogen is just doing the same process we talked about, electrolysis, but taking the electricity from, rather than renewable sources, taking it from nuclear energy, and you still produce waste product, but it's different waste product. There are many other kinds. Salmon is taking plastic waste and processing it. Yellow is the same process, electrolysis, but using the electricity from the grid, which largely comes from coal, natural gas, and nuclear. Increasingly renewables as well, but still a minority. We have fairly recently discovered something called white hydrogen, which is occurring underground naturally, and we didn't hardly know it existed or in any quantity. But since we started looking for it, we've found out that there are actually quite a few sources of white hydrogen, but they aren't very conveniently located. And so you would have to truck them, train them, pipeline them to where they're needed. And of course, finally at the bottom is green hydrogen using just water and electrolysis only from renewable energy that is created specifically for the process. It isn't good enough to take renewable energy that's already on the grid and was designed for some other purpose and use that, because if you do that, all that happens is that they run the coal and natural gas power stations longer, and you still get the extra CO2. Okay, let's see if we can move on from here. We've already covered this. The numbers about what percentage is coming from black and gray and brown, black, vary a little bit according to the source you get it from. What we have to watch out for is our greenwashing being done by the industry. All these middle grounds, all of which have significant waste product. Some of them, they're just environmentally undesirable in the sense that the energy that is involved in them makes the process dirty, even though it's producing hydrogen at the end. None of these are clean. Just watch out for that as a greenwashing. And then concentrate on the white to the extent it exists, and then the green hydrogen. And one of the reasons for why there's so much dispute over here is the price of these things. They're all different prices. So if you start off with the cheapest one, you can get a liter of a kilogram, I think it is, of black or brown for $1.25. but it'll cost you from $4.92 to $11.96, depending on the source of your electricity and the catalysts you use and so on, to get green hydrogen. So, of course, the industry would like to do brown and gray. They're being pushed strongly towards blue to get a capture of this carbon dioxide, but that increases the price by more than twice. And we would like them to go all the way to green because that would eliminate the need for pipelines, eliminate the need for all the other processes that go on in the capture and the transportation of CO2 and hydrogen. Okay, where is this hydrogen going to? Well, today, about 50% of the hydrogen being produced goes into another process where we combine the hydrogen with nitrogen from the air to make ammonia. Ammonia has several purposes. Most important one is for fertilizer, widely used for fertilizer, ammonia or urea, made from ammonia. And the other 40% of it goes, or the next 40% goes into refineries, petroleum refineries, to hydrogenate the petroleum products and make them more suitable for use, get you a higher yield of the products you really want. The rest goes in a variety of different things like glass. Some electronics uses it, but particularly as a coolant. If you want to get really cold temperatures, starting off by making liquid hydrogen is a good place to start. The bottom diagram shows a thing called the Haber-Bosch process, which is widely used to make ammonia. You pump in the natural gas and the water at one end and the energy, add some oxygen and nitrogen from the air, get the hydrogen out of that, then you combine that with more nitrogen from the air, and out comes ammonia at the end, which is NH3, 3 hydrogens, 1 nitrogen. Okay, so since this has been basically dormant or very small factor for many years, why is that, and what are the problems that face making hydrogen a major energy component for us in the future? 5 things we're going to look at. First of all, the safety. Secondly, the way it's produced. Next thing is, how do you move it around? What's the transportation issues? How do you store it? And what's the climate impact of using it? Deal with safety first of all. As you probably know well, hydrogen and oxygen combine explosively. On the right-hand side, you can see the Hindenburg disaster from 1937, where the airship caught fire inside, and the hydrogen in its cotton-lined plastic bags, or material bags inside there, the hydrogen caught fire, exploded, and many people died. One of the problems with safety is that whatever you keep it in, pipelines or containers and so on, makes the metal brittle and more likely to break. And the more you keep it around, the more brittle it gets. And if you're going to use it, therefore, in a situation where the public is involved, you're going to need a whole lot of very, very careful procedures to make sure that you don't get into safety damages with it. Here's the reason why it's so flammable. If you look at methane, natural gas, it'll only catch fire if the concentration is between 5% and 15%. If it's less than 5%, it won't catch, not enough there. If it's over 15%, there's not enough oxygen around to make it burn, and it won't burn. Hydrogen, on the other hand, is very flammable over a whole range of concentrations. So from 4% to 75%, the hydrogen will go poof at the slightest excuse. And so any leak of hydrogen, a small one or a larger one, is more than likely going to catch fire and explode with an enormous amount of that energy we said was stored in it coming out in a hurry. Let's talk about production. As we've said, more than 90%, maybe 99% is coming from fossil fuels now. the electrolysis of water, as you could see, is significantly more expensive and I'm not sure about less efficient, but it is not as practical at the present moment. There are various other options, including white hydrogen, but right now, as I say, the vast majority is made with natural gas, and the fossil fuel companies would very much like to keep it going that way by just clipping on carbon capture. Transportation. We've talked in the past about how few miles of carbon dioxide pipelines there are, about 5,000, but the number of miles of hydrogen pipelines is less than 1,500. And the main reason is that the stuff is not easy to move around. And so most of the places where it's needed, they just put up a hydrogen plant alongside their other facility, there, the refinery or whatever it is, the ammonia plant, and make it on the spot and use it immediately. So it doesn't spend long in pipelines or in containers. And that's not very practical if you're going to try and use it for long distance trucking or things like that. Of these 1,500 miles, only 3 operators really run 85% of that mileage. And so there's not a whole lot of skill and experience with operating long distance or large hydrogen pipelines. The ones that do exist are either they're very, very short inside plants, or they're rural and very small diameter and therefore easy to make strong. This stuff does fall under PHMSA regulations, but there are no specific regulations for hydrogen pipelines at this time. You can see we've, in the comparison to natural gas lines, we had 300,000 miles of those and 2.3 million miles of distribution, which is the local pipeline. So we have tons of experience with these other kinds of gas pipelines, but not with hydrogen. The only real hydrogen pipelines of any significance are down in the Gulf, Houston across to New Orleans. These are active pipelines, and a little one around Corpus Christi, and a little tiny one over Mobile. So you can see how limited the extent and experience of these pipelines is. Okay, so moving on to moving it around. Hydrogen is a very, very small, it's the smallest molecule that exists in a stable form. And not only is it tiny, but it's also slippery. It doesn't bond to many things that will cause friction when it tries to escape. As we've mentioned, it causes the steel to get brittle, and that's true for both steel and polyethylene pipes, which are used when it's just a gas. And unlike most other pipelines, where the harder the steel is, the more likely it is to survive for a long time. In hydrogen, because of the embrittlement process, softer steel lasts longer. What that means is that existing pipelines cannot readily be converted to hydrogen. Hydrogen is very prone to leak. If you put hydrogen in a pipeline that used to carry methane, there'd be a much greater volume of hydrogen leaking than there was of methane. And although it's a very light product and tends to go up in the air and dissipate fairly quickly, it can leak underground when you've got a pipeline, buried pipeline, and it tends to accumulate in underground before actually exploding. And it will, as you said, more likely to explode than methane in the same volume would do. It's gone into storage. If you're going to have hydrogen operations all along the motorways, which is what the industry would like to do for heavy truck transportation, possibly use in shipping and so on, you have a storage problem. It takes 11 cubic meters, which is a lot of space, to 33 feet on each side, a cube that big or more, to store just 1 kilogram of hydrogen at room temperature and pressure. And so people don't do that. So you have a choice. You can keep it as a pure gas, but under high pressure, or you can liquefy it. If you compress it to get any useful storage compaction, you will need to put it to 10,000 pounds per square inch, which, bear in mind, we said that we were concerned about CO2 pipelines at 2,000 pounds per square inch, or even natural gas pipelines, which typically are not more than 700 pounds per square inch. So this is really, really high pressure, requires very special treatment, very thick steel, and so on. And if you want it liquefied, you have to get down to minus 253 degrees centigrade. And for those of you who weren't physicists and chemists, remember that minus 270 degrees centigrade is what's called absolute zero, and nothing will get colder than that. So all motion of the molecules is stopped and so on. That's 423, minus 423 degrees Fahrenheit. It's extremely cold. And again, embrittlement happens down there. And it does get absorbed into the materials and chemically bonds and so on with them. So, as I said earlier on, for a space flight center like Kennedy, you can put together the kind of equipment like this is on the right, where you can store this hydrogen safely when you need it. But for everyday use alongside your motorways, not a good idea, probably. Okay, so I've hinted at some of these things before. How does the industry and how does the government envision that we're going to use all this hydrogen that they're spending these billions of dollars to make? Fuel is probably the most common use, because if it's burned in oxygen, hydrogen only produce water as a byproduct. So there have been projects for years, primarily in Japan, to make cars that run on hydrogen. But as you saw in that first graph I showed you, the density of hydrogen is extremely low. So the amount of hydrogen you have to carry around to get a reasonable amount of distance out of your car is quite high. And you have to store it at very high pressures, which means you've got to have very strong tanks in the car that you can load up with hydrogen. And for cars, because of the energy density issues, hydrogen is not really a very practical solution. And of course, the infrastructure for refueling them just doesn't exist anywhere really in the world. There's little pockets like Southern California where there are hydrogen refueling stations, in Japan, but very, very few. And to say there's a major obstacle to creating widespread availability of hydrogen anywhere. You might put a hydrogen generation plant through electrolysis in every truck stop along the highways, but that still wouldn't get you all your cars refueled with it. There have been other proposals to convert your locomotives to use hydrogen. There are two ways we can use it in these vehicles. You can either take the hydrogen and put it through sort of a reverse electrolysis process and use it to generate with oxygen from the air, generate electricity and run the cars and trucks with electric motors. That's very clean. It's not super energy efficient, but it's a definite possibility. The other approach, particularly for heavy vehicles where there's a lot of investment already in place, you could do a conversion of your existing diesel engine to run on hydrogen. So it's another internal combustion engine, but using hydrogen as a fuel. But any time you start burning a fuel, no matter what it is, the efficiency goes down. You lose 30 or more % of the energy in the hydrogen or in the gasoline just because you're burning it, creating lots and lots of excess heat that you cannot use. So the preferred method of using hydrogen will be to go through a fuel cell and convert it into electricity and then use it for driving the motors. Now, for a locomotive, that's not too bad because most of the locomotives are already running on electric motors. They're just powered by diesel generators with diesel engines with generators behind them to power them. So you could swap out the diesel engine, put in a hydrogen fuel tank and a fuel cell, and run the locomotive much as you do now. And that might be cheaper and less energy intensive than stringing electric wires all along the whole distance of the railway tracks. That's done in Europe, been done for years, and in Japan and in China and so on. They bit the bullet and made all their high-speed locomotives electric, and they had to wire all their railway tracks with that. But it's not easy and cheap and so on. Another possibility is ships, and again, the two alternatives are available as well. Ships, by and large, don't use electric motors, so they might be inclined to try and run with their existing diesel-powered engines with modifications, or new engines possibly. But they only refuel at a certain number of places, so the refueling problems aren't so bad for ships. One of the most challenging fuel issues is airplanes, because they have to be very light. They want to be refueled very quickly and have very reliable sources of energy. And please don't do a Hindenburg on us. And there are examples of people trying to do this, but nothing practical in any long distance plane is anywhere on the horizon. You aren't going to be crossing the Atlantic on a hydrogen powered plane, probably in my lifetime, which isn't saying much. Okay, so those are the fuel uses. The other possibility is energy storage. This is very important when we're using renewable power from solar or wind. There are times, sometimes long times, sometimes 3 weeks almost, when the wind doesn't blow and the sun doesn't shine, and your lithium batteries just aren't big enough to power the whole state or whatever it is for long periods like that. So we do need to have some way of putting power on the shelf, so to speak, indefinitely, so that when it's needed, we can turn it back into electricity. And hydrogen storage is one of many ways it's being looked at to do that. There are many other kinds of batteries, like flow batteries and water batteries and so on, and compressed air batteries, which could be another alternative. But hydrogen storage is one way that you can, with relatively high efficiency, take the excess power available when the sun is shining and the wind is blowing like mad, and store the excess power into hydrogen, then reuse it when you need it. The other very dangerous thing that's being considered, and this is primarily greenwashing, is to make natural gas clean by mixing 10 to 15% of natural gas, of hydrogen in your natural gas, and just injecting that into the normal gas pipeline distribution system. But we know already that the existing distribution systems for natural gas leak like a sieve. There's a vast amount of methane being leaked out of the natural gas distribution system. And if you put hydrogen in it with it, that's going to leak even worse. And the energy you saw from hydrogen at a gas point is much lower than the energy you get from natural gas. So you'll actually have to use a larger volume of gas to get the same amount of energy out than you would do if you just burned natural gas normally. There are all sorts of problems with mixing hydrogen in any reasonable volume, and it doesn't achieve the result of making the whole process clean at all. It just slightly reduces the excess of CO2 produced. Okay, so we already mentioned this. How do we convert this hydrogen into useful energy? It's not very useful in its hydrogen form. Two ways of doing it. You can either go into a fuel cell and combine it with oxygen from the air and don't burn it, and it's about 70% efficient. Alternatively, you can adapt your engines or furnaces and so on to modified internal combustion engines, and you get about 30% efficiency. So very, very bad efficiency if you just kind of go back to the old ways of doing things. Here's sort of the industry image of how we are going to make this economy. It's a really idealized and unrealistic image. First of all, you start by taking sunlight, which is solar energy and wind, and use that to drive your electrolysis process, out of which you get oxygen, which you can release into the air, and hydrogen. You move the hydrogen into hydrogen storage wherever it's closest needed, and you just pump it into your cars or your vehicles and so on, and use it in fuel cells. Very nice, very clean process, but there are significant problems in the storage, as we saw, significant problems in the transportation. Here's the big one at the moment. This is that 1 inch long thing on the diagram, which will be hundreds of miles long or thousands of miles of hydrogen pipeline to distribute this around the country. And the practicality of doing that is very questionable. Hydrogen uses energy storage here. We've covered this pretty much. When the sun doesn't shine, the wind doesn't blow for more than 8 hours at a time, up to 19 days. We've got examples of that. Existing approaches for storing electricity just don't work. We have to have dependable electricity. So we take the power in from the wind farm, go through an electrolyzer, split off the oxygen from the hydrogen, take the hydrogen in storage at 30 atmospheres pressure or something like that, and store it until we need it. It's still a gas. It's not going to be a liquid at that point, not very highly dense. So we need a good sized volume for that tank. Then we go through the electrolyzer in reverse, called a fuel cell, and out comes electricity. And of course, if you need the electricity, you can bypass all that step and go straight from the wind turbine to the utility grid and so on. The hydrogen cost itself is high from electrolysis, takes a lot of electricity to do it. The storage cost is high because of the high pressure, low temperature, and the round trip efficiency is not very good, but there aren't that many alternatives yet, but we're working on them very, very hard, and we anticipate that we'll get lots of other alternative approaches, which may be better than this one. This is just more on the natural gas dilution for domestic use. This is the industry vision. You take the natural gas from the grid that's already there. You use natural gas power and lots of water to go through that harbor process we talked about, create hydrogen dioxide, and you throw off the carbon dioxide, capture that. You move it around to wherever it's needed, and you put it into the natural gas distribution line so it can be used in your house. It's pure and simple green lighting, no practical benefits to anybody except the gas companies who get to use their existing gas distribution networks for a few more years and say that it's clean. Anything over 20% of hydrogen in the natural gas stream requires you to go into every gas appliance you have and modify the burners. So that's an enormous process, and as you can imagine, very hard to switch over from low to high concentrations. High pressures in your gas distribution line because you need more gas to be moved than you had to have before. Different pipes and valves sometimes are necessary, different welding techniques, all sorts of problems. Deodorants that you use on natural gas, which is mercaptan, doesn't work with hydrogen in there. The pipelines degrade more rapidly, but the gas distribution companies are desperate to keep their existing pipelines, to keep themselves in business, and move away from the conversion to 100% electricity. So they'll do anything to make it look like they're being green. Okay, so this is just more details. Lower density, as you saw, can't do a one-for-one migration. As you migrate more hydrogen, you need more volume of gas. And so a 10% hydrogen blend would not save you 10% of the greenhouse gases. You only save 3%, and that doesn't account for at least leaks of hydrogen and methane through the pipeline system. Okay, looking at the climate impact. Hydrogen itself can leak more rapidly than methane. And hydrogen itself is not a greenhouse gas, but it has the same effect in that it will change the way that methane degrades so that the methane degrades more slowly and it's already more damaging than CO2. So by making it degrade more slowly, it results in having 30 times the warming power of the same volume of CO2 for the first 20 years. And the leakage will erode the climate benefits that you expect to get and claim to get, and will actually maybe make the climate change worse than it would be without hydrogen out there. Safety recommendations have been produced by a number of organizations. I think these come from the Pipeline Safety Trust. First of all, no blending, prohibit blending in domestic distribution systems. PIMSA has to go in and really do the same thing they're doing for hydrogen that they're planning to do for CO2, is document the way that hydrogen blending can be used if it's used at all in a transportation pipeline. That's the big distance pipelines. We should not try and repurpose existing transmission lines for hydrogen because the hydrogen will not likely stay in them. It was bad enough when we tried to repurpose them for carbon dioxide pipelines, but it's worse with hydrogen. PIMSA should require the gas transmission pipelines convert and transport hydrogen to do very, very thorough testing of the pipelines before they put the hydrogen in them. And we need a whole lot of regulations about pipelines regulating CO2 hydrogen. Okay, I want to give credit to a number of people whose slides I plagiarized to this presentation. Mark Jacobson, who is, as you probably know, from Stanford, and has produced some magnificent books and studies on all manner of issues in dealing with climate change. This is the one that I found most useful for this presentation. The Australian Earth Science Institute also has some very good presentations on this subject. Bill Karam, our friend from the Pipeline Safety Trust, has contributed a number of the slides here. Jane Patton, who's made an excellent presentation to our CO2 plenary group. She's from the Center for International Environmental Law, SEAL, has some great stuff on hydrogen pipelines. And there are various other sources of hydrogen there. So I think that's these are the references from the Pipeline Safety Trust. More of those there. You can get an entire slide presentation, not this presentation, but another one from that link at the bottom there. And thank you very much indeed for your attention. There's a lot of detail thrown at you here, but this is a growing field. You're going to hear a whole lot more about this in the future. Thank you so much.